Alright, so I'm going to continue from where I left off in the last video and go over how to calculate the freezing point depression and boiling point elevation. So there's a few different things for what you can be solving for. So you can be solving for the change in the freezing point. So that's what this represents. Or you can be finding the new freezing point. So the K of F value, which you need to calculate the change in freezing point, is a constant that I will provide to you. And you can find that on this chart right here, okay? And I'll go over that in just a moment when we get to the example problems. And then you have, of course, the little m, which is molality. Don't forget molality is calculated by doing the moles of the solute divided by kilograms of the solvent. And usually the solvent will be water. I do have a couple other examples here besides water that you can come across, but these would be your solvents. And usually the solvent is what you have more of, and the solute is what you have less of. Now this equation is for non-electrolytes. Non-electrolytes are pretty much any compound that is not ionic. So things like carbon-based molecules like C6H12O6, which is glucose, that would be an example of a non-electrolyte. Versus electrolytes, these are all your ionic compounds. So anything with a metal and non-metal. So an example would be NaCl. And when you have a problem where you're dealing with an electrolyte, you just have to take one more step to find I, which is the total number of ions that form during dissociation. And I'll go over that in the example problem. To find the new freezing point, you would just take the normal freezing point, which again, that is on this chart here. So you have normal freezing point, normal boiling point, and you would just subtract the change in the change in freezing point. So make sure though when you plug in delta T of F that it is a positive number. Because your new boiling point should be lower than the normal freezing point. Okay, so the normal freezing point, when you get your new freezing point, it should be lower than what you started with. For boiling point, the opposite is true. You're going to have a, for the new boiling point, it's going to be higher than the normal boiling point. And you, again, just add this value and it will be positive. And pretty much the same thing. The only difference is instead of K of F, you have K of B. There is a typo right here. These should be B's because we're talking about boiling point. So now let's go over some examples. One thing I will note is that in the examples I tell you if it's an electrolyte or not. But on a test, I won't tell you if it's an electrolyte or not. Again, pretty much the difference is an electrolyte is an ionic compound, while a non-electrolyte will be some really big carbon-based molecule like glucose, okay? And then also, the solvent won't always be water, but for a majority of these examples and what you'll see on the test, it will be water. So here's that chart. On your test, I will just give you the value instead of you having to go find it on this chart. But when you're doing your homework, you will have to use this. So water will be the main one that we will use for most of these examples. All right, so for the first example, we have to find the change in freezing point, and I will also show you how to find the new freezing point. And you can also cross off this problem right here. So I'm going to show you how to do both within the same problem. Also on the test, I will give you the molar mass, again, just to save time because these are pretty lengthy problems. So what is the change in freezing point? And we will find the new freezing point. If you have 35 grams of NaCl, which is sodium chloride, which is an electrolyte because this is an ionic compound, and it's dissolved in 750 grams of water. That is the solvent. 1, because it's water, and 2, because you have more of it than the solute. Now, you can go into many different orders as far as like what you're solving for first, but I like to start with finding M, which is molality. Again, we're trying to calculate this right here, and we know what this value is because of the chart. And I'm going to start with finding M, which is molality, and then I'm going to find I, which is the total number of ions, because this is a electrolyte. So let's start with little m, which is molality, which is moles over kilograms. So we first have to find moles of the solute. So our solute is NaCl, and we have 35 grams of that, and we need to get it into moles first. And I have provided the molar mass, 58.44 grams, excuse me. All right, we're going to set up our picket fence. So 35 divided by 58.44. For this part, you can round 2 decimal places. So I'm going to do 0.60 moles. And then I have to find kilograms of the solvent. Now notice for water, I did give it to you in grams. So in order to get grams into kilograms, you have to move the decimal 1, 2, 3 places to the left. So for my solvent, I have 0.75 kilograms. For my solute, I have 0.60 moles. So I'm going to do 0.6 divided by 0.75. And again, you can round 2 decimal places, that's fine. So 0.8 little m, which is the molality. So now I have to find I, and in order to do that, I have to do, and again, this is why we did disassociation. We have to disassociate NaCl and find the total number of ions that will form. So I have 1 NaCl, or I'm sorry, 1 Na, which is sodium. You can put a 1 here if you want. Plus, you'll have 1 chlorine ion that will form. Again, because you only have 1 of each of these on this side. So we're simply going to do 1 plus 1, which will give us 2. And 2 is your I value, okay? So you just add up the total number of ions that you get from disassociating the solute. So now we can find delta T of F, which is the change in freezing point. So we're going to do K of F, which we get from the chart. So for water, that is negative 1.86. So we have negative 1.86 times the M for molality, which we calculated to be 0.8, times I, which we got 2 for. So our delta T of F, we will get by multiplying these all together. And I'm going to round 2 decimal places, 2.98 degrees Celsius, okay? So this will change and it'll decrease by negative 2.98 degrees Celsius. So if you're dealing with water and you're trying to find the new freezing point, it's actually pretty straightforward. So the new freezing point you find by simply, this equation is on this slide right here, by taking the normal freezing point minus the change in freezing point, which makes sure that is a positive value. So the normal freezing point of water, again, if we look at this chart, normal freezing point is 0 degrees Celsius. So you would simply just do 0 minus 2.98. Make sure that's a positive value. So you will get negative 2.98 degrees Celsius. Yes, I realize both of the answers are the same, and it's because the freezing point of water is 0 degrees Celsius, and when you add a solute to a solvent, it will always decrease the freezing point, and our change was 2.98 degrees Celsius. So our new freezing point would be negative 2.98 degrees Celsius. So that's pretty straightforward. as far as when you have water as a solvent. So now I'm going to do another example, but this time we're going to find the boiling point, and I'm going to show you how to find the new boiling point. Now this time we are dealing with a non-electrolyte. Again, if you see a big carbon-based molecule, sucrose, glucose, fructose, whatever it might be, usually a sugar, that is a non-electrolyte. This is something, again, that is not an ionic compound. So notice we don't have the I here because it is not an ionic compound. So what will the change in boiling point be? And we will find the new boiling point if 50 grams of sucrose is dissolved in 500 grams of water. Again, water being our solvent again this time. So the first thing we're going to do is find M, which is molality, moles over kilograms. Again, we don't have to find I this time because it is a non-electrolyte. So to find moles of the solute, we have to take those 50 grams of sucrose. Again, that is your solute. Water is the solvent because, well, you have more water than you do the solute. So the molar mass of that I have already provided to you, 342.3 grams. 1 mole goes on the top. Again, grams to moles, picket fence. We've done this many times. So I'm going to round 2 decimal places, so 0.15 moles. Now, again, for the water, it is in grams. I have to get it into kilograms, so I'm going to move 1, 2, 3 decimal places to the left. So I will get 0.5 kilograms of water for my solvent, and I have 0.15 moles of my solute, and I'm going to divide those, and I will get 0.30 M, which is our molality. So now I can find the delta T of B, the change in boiling point. So that's K of B for, again, water. So going back to this chart here. So that is 0.51. So I have 0.51 times the molality, which we calculated to be 0.3. I'm going to multiply those. So my delta T of B is 0.15 degrees Celsius. So not a huge, like not even a degree change in the temperature. So now to find the new boiling point, we have to take the normal boiling point of water, which if you look at this chart here, the normal boiling point of water is 100 degrees Celsius. That's what water boils at. Plus these change in our boiling point, which was 0.15. So again, when you're dealing with water, finding the new and the new freezing point and boiling point is pretty easy. So 100.15 degrees Celsius, because again, when you add a solute to a solvent, it will increase the boiling point and it will decrease the freezing point. And that's how you calculate the new boiling point, change in boiling point, new freezing point, and change in freezing point. These two examples down here, you can cross them off and skip them. That's not something that you have to worry about. If you do want more practice, though, I recommend going back to the videos, the Professor Dave video. He actually goes over 2 examples, so you can do those on your own, and then he shows you the key for them if you feel like you need more practice.